something bad. We don't want that. We said that in terms of asymptotic complexity, we only care about that. But when sometimes the constant factor is too high, maybe we start looking for another algorithm which is log linear but has a smaller constant factor. Okay, what I'm trying to say is merge sort has, for example, let's say a complexity of 1000 n log n. If we find another algorithm which has complexity 10 n log n, then obviously this algorithm is going to be better because it has a smaller constant factor. Although both of them are big O of n log n, so they have the same complexity, this one is practically better than this one because it has a smaller constant factor. So this is why we are talking about the weaknesses of merge sort, because we want to find out whether or not we can find a new sorting algorithm which is better than merge sort. Now there is a result that we are going to state without proving. The result is there is no sorting algorithm based on comparisons like we are doing. We are comparing elements to each other. There is no sorting algorithm based on comparisons which is going to be faster than n log n. Okay? Or has a growth slower than n log n. Okay, let me not confuse you. There is no algorithm, sorting algorithm, which is based on comparisons and is more efficient than n log n. So that's a result. Now, what does that mean? I'm using this operator, which we have seen. It's called big omega. What does that mean? Is that for any sorting algorithms, which is based on comparisons, like we did, what does it mean based on comparisons? We are comparing keys to each other. Now, there are other sorting algorithms which are not based on comparing keys to each other, okay? But they are not general sorting algorithms. You cannot always use them. You only use them in specific cases. For example, the input has only 3 different values. If your elements are either 1 or 5 or 100, if all the elements in the sequence are either 1 or 5 or 100, then you can sort these in almost linear time. But this is a special case. So the input is obeying a very special case, which is, in this case, the input has the following property. All elements, they come from 3 different values. So if you have another 4, they come from 3 different values. So if you have another 4th value, you cannot use this algorithm anymore, this sorting algorithm anymore. So we are not discussing these in the lecture. In the lecture, we are discussing only algorithms which are based on comparisons, i.e., the sorting algorithms that you can apply for any kind of input, not for specific kind of input. So for general sorting algorithms, which must be based on comparisons, we can never get a sorting algorithm which is faster than n log n. Basically, we cannot find an algorithm which is big O of n or big O of log n. So we cannot find something like that. However, we have said that merge sort is n log n already. Okay, merge sort is n log n. Now, does that mean that we should stop searching for a new algorithm? Because if merge sort is already actually big theta of n log n, and I have said that we cannot be better than that, so do we stop thinking about algorithms? Well, the answer is no, because merge sort has this problem. It has 2 problems. One, it has a high constant factor, and the other one is The other one is it requires big of an extra space. Are these two problems clear? Yeah. Somebody said meow. So what is not clear? So merge sort has a high constant factor and it needs big of an extra space. Which of these is not clear? They are clear? Okay, whoever says no, please say what is not clear. I mean, I don't have crystal ball. So, what is not clear? Could you speak up because I can't hear you? Oops. Is somebody in the process of speaking now? Okay, I mean, I have already explained this in two different ways for each bullet point, so I do not have another way of explaining it. So if you don't point out to me what is not clear, I cannot explain it a third time. So you either tell me what is not clear, or we're just going to move on. So we are going to move on. So the merge sort is n log n, and we cannot have something better than n log n. However, merge sort has two problems: a high constant factor and an extra space of big of n. So if we find a sorting algorithm which is n log n and either has a lower constant factor or doesn't use big of n space, or doesn't have a constant factor, a high constant factor, and does not use a large space, then it is going to be better than merge sort. So this is the thinking now, okay? So this is why we want another algorithm, because our current one, although it is going to be the best in terms of asymptotic complexity, it still has problems. If we fix them, we are going to find an algorithm which has the same asymptotic complexity, but practically it's going to be better because it doesn't require space, or it doesn't have a high constant factor, or it doesn't have both of them. So now we start talking about another sorting algorithm, which is quicksort. So quicksort works in kind of the reverse way compared to merge sort. So merge sort splits the sequence and then do the merging, but quicksort merge sort splits the sequence and then do the merging, and while it is doing the merging, it is doing the sorting. Okay, so merge sort does the sorting part in the merging part, because the merge routine takes the subsequences and order them. So the sorting part in merge sort is done at the merging part. Okay, let's put it another way. The sorting work in merge sort is done at the merging part. In terms of quicksort, we also have partitioning and merging, but the sorting task is done at the partitioning part. Okay? So this will help you visualize the difference between the two. So we have merge sort and we have quicksort. we have first partitioning, and then we have partitioning, and then we have merging, and quicksort we also have partitioning, and then we have merging. In merge sort, we do the sorting here in the merge routine. In quicksort, we do the sorting here in the partitioning routine. Okay, so both of them are divide and conquer, but the real work in merge sort is done here, but in quicksort it's done here. So this is merge sort, and this is quicksort. Merge sort, we have seen, it's a divide and conquer algorithm. It splits the sequence into until size 1 here, and then starts merging. While merging, it sorts the subsequences. Before putting two subsequences together, it sorts them. It takes the smallest element of each of them and put it in a third sequence, and so on. So the sorting, as we have seen, happens inside the merging. In quicksort, the sorting happens at the partitioning before the merging. The merging is the easy part, the partitioning is the hard part. Here, the partitioning is the easy part and the merging is the hard part. We will see the examples. This was just meant to give you an overview before we dig in more into quicksort. So, let's see how this works. So, we have an initial sequence, as you can see in front of you, which is the same sequence that we have used in all sorting algorithms. We are going to choose one element of this sequence. We are going to call it the pivot. Okay, we choose one element of the sequence. We are going to call it the pivot. Now, what is this element? For now, let's assume this element is the first element in the sequence. So the first element in our initial sequence is 9. So we are going to say 9 is the pivot. Now what is the pivot? The pivot is one element that we are going to use in order to divide the sequence. So in merge sort, we divide the sequence in half. In quicksort, we are going to divide the sequence into 3 parts. One part, the middle part, which contains the pivot. The other part to the right contains all the elements which are larger than the pivot, and the part to the left is going to contain all the elements which are smaller than the pivot. Okay, so we read the sequence from left to right. So first the pivot, we put it in the middle, and then 4 we put it to the, and then 4 we put it to the left, 8 to the left, 7 to the left, 1 to the left, 6 to the left, 2 to the left, 5 to the left, 2 to the left, 10 to the right, 5 to the left, and 3 to the left. Okay, so we partition, we split the initial sequence into 3 subsequences. The left hand side is the sequence that contains all the elements which are smaller than the pivot. The right hand side contains all the elements which are larger than the pivot. And we recursively continue doing that until we reach sequences of size 1. Okay, so this is a sequence of size 1, so we cannot do anything further. Now let's have a look at the sequence. We pick the first element. We choose the pivot. It is going to be 4. Now we are going to divide the sequence around the pivot. Okay, so we are going to read the sequence from 4. So 4 is the pivot, it goes in the middle, and then we have 8 goes to the right, 7 goes to the right, 1 goes to the left, 6 goes to the right, 2 goes to the left, 5 goes to the right, and 3 goes to the left. And we get this level here. And we continue for subsequences of size more than 1. So 1, 2, 3. 1, 2, 3. So we choose 1 as the pivot. We put it in the middle, and then 2 goes to the right, 3 goes to the right, and there is nothing to the left. So this symbol here means an empty set. There is nothing. And we continue for 2, 3, and we continue for these and so on. And then all we have to do is to merge these elements which you see here. So this is the empty. This is 1, empty, 2, 3, 4, 5, 6. This is 7. This is 8. This is 9, and this is 10. As you can see, we have already sorted the algorithm, the sequence. Okay. So all we have to do after we reach subsequences of size 1 or 0, what we have to do is to merge. It's just to merge, just to merge these values. And as you can see, they are already in a sorted fashion. And the merging is not like merge. It's not like merge sort. The merging is easy. We are just putting elements together. We are not doing any work. Most of the work we have done it at the partitioning level. But at the merging level, we don't do anything. We just append, concatenate, put together the elements. So this is the view I tried to explain to you in the notes. I said merge sort has an easy partitioning and a hard merging. Quick sort has a hard partitioning and easy merging. Quick sort has a hard partitioning and easy merging. So that's how quick sort works. That's the pivot. Basically, we choose an element that we call the pivot, and we split the sequence around that pivot recursively until we reach subsequences of size 1 or 0. The position of the pivot can be anything. In this example, we have assumed that the pivot is the first element. It can be the last element. It can be a random element, and we are going to see how the position of the pivot is going to affect, not the position, how the choice of the pivot is going to affect the complexity of our sorting algorithm. So that's quick sort in an example. So let's have a look at the code. The code is pretty much easy. So we stop the recursive call when the size of the array is 1 or 0. And then we choose the pivot. We have in this case decided that our pivot is going to be the first element in the sequence. And we are going to partition the sequence A with respect to the pivot and obtain 3 different arrays. A1 of elements which are smaller than the pivot, A2 of elements which are equal to the pivot, and A3 of elements which are greater than the pivot. And all we have to do is concatenate or append or put together the middle one with the quick sort of the left one with the quick sort of the right one. This is what we've been doing here. So what we are concatenating here, we are concatenating, for example, at this level, we are concatenating the quick sorted version of this, the quick sorted version of this with the quick sorted version of this with 4. Okay, the quick sorted version of that is obviously this. So this is just the recursive definition of quick sort. I call it the naive quick sort. This is the simple quick sort, which is not the best one. It still has problems, as we will see. But this is our way into understanding the quick sort algorithm. So that's the first version of quick sort that we are going to see. It's the most intuitive version that is going to help us visualize or prepare us for the next more complicated version. So that's what I call it, the naive simple quick sort, and that's the same one with comments. So Um, okay, let's talk now about the complexity of quicksort. So let's look again at the diagram here. Now, we said that what is the number of partitioning levels of merge sort? What is the number of partitioning levels of merge sort? Are you generating random numbers or something? Okay, what is the number of partitioning levels of merge sort? I'm gonna cry. Big off. Oh my god. I give up.
No, don't give up. You will give up.
Seriously, I mean, I've been repeating this all morning. What's wrong with you guys or girls? What is the complexity of? Okay, what is the number of merging levels, please? What is the number of partitioning levels of merge sort? Yes, log n. Yes, log n. Why is this so hard? So in merge sort we have log n partitioning levels. Okay, log n partitioning levels. Always visualize the sorting algorithm in front of your eyes, and if you cannot find the answer, use numbers. Numbers never lie. Use numbers. Imagine an array in front of you of size 16, and imagine how many levels are we going to have in order to finish partitioning. In the worst case, it's going to be log n. Now, what is, in your opinion, the number of partitioning levels of quicksort?